I'm Max Carson, and this is my creative project, multi-layer Perlin noise terrain generation coded in Python. My whole life I've loved taking stuff apart and learning how things work. Over the past couple of years, I've grown an interest in computer science and robotics, leading me to teach myself Python, HTML, CSS, and JS in the Arduino subset of C++, along with a little bit of electrical engineering. Earlier this year, I was watching a video where a game developer created a game with procedurally generated terrain. They mentioned that the way they created this terrain was by using Perlin noise, which is a type of gradient noise invented by Ken Perlin in 1983 because he was tired of computer generated images looking bleak or unnatural. It is essentially a 2D list or grid of values that, when displayed, look like terrain or something natural. It is mostly used in video games as it is completely random and can be generated infinitely. The game developer I was watching used a built-in function to generate the Perlin noise and didn't do it on their own, so I took it on as a challenge to code it completely from scratch, and I already had an idea on how I might go about creating it. I wanted to do this entire project without tutorials or any research at all, at least at the start, so I went through a few iterations and got pretty close, but I couldn't get it quite how it was supposed to look, and it had a weird pattern. Nonetheless, I was pretty happy with what I had figured out on my own. A while later, I saw a video of someone making a project in Unity, a game engine, and noticed they had used Perlin noise. But like the last developer, they also used a built-in function to generate it. However, they did give a rough explanation on how it worked. You generate a grid of random numbers, as you can see here, and then to smooth it, you go to each individual value and set it to the average of all of the values around it, as you can see here. You repeat this smoothing process or iteration as many times as you want, changing the intensity of the noise. This image over here is after about 40 smoothing iterations. This is almost exactly what I had been doing earlier, except I started with an empty 2D array, not one filled with random values, and then I went left to right on every row, getting the averages of the filled-in spaces around the value. Generating the noise in this manner had two flaws. One, because the values below and to the right of the current value had not been defined yet, I could only get the average of the ones above and to the left, leading to a pattern that goes diagonally across the screen and isn't smooth like intended. Two, I couldn't go through multiple smoothing iterations because it didn't have much of an effect, and I wasn't even aware that this was a possibility at the time. Without this, I wasn't allowed to make different intensities of noise for different purposes. With this newfound knowledge, I went back to work and started to implement everything I found out. I even added a few of my own parts, like a bit of random change when I generated the average value so that there was a bit of variation. This worked for the time being, but I ended up changing in the end. Through some trial and error, I figured out how to code it completely from scratch in Python. A lot of it was pretty tricky and complicated, like accounting for corner and side values, because they weren't completely surrounded by other values, but I eventually got through all of the errors and finished with a working Perlin noise function. I then thought looking at a big array on a console was pretty boring because you couldn't really tell what it was showing. For reference, this is what I had been looking at up until this point. So I made my own function that could display any size of 2D list containing any numbers by using the Pygame library to create a graphical representation of it. It worked by calculating the minimum and maximum value in the list and then converting every value down to a range of 255 so it could be used in RGB. By doing some math to determine how far apart the squares containing the color had to be and the size of them, I was able to display the noise in an easy to see and understand fashion, and I could change the screen size and array size with the function automatically adjusting. By this point, I had achieved exactly what I was looking for and was extremely happy that I had figured it out with no tutorials or any research at all, or close to any. I was curious what I could do with this noise, so I decided to try converting the different intensities into different colors to represent real terrain, like water, land, and mountains. This was super cool, but it didn't quite look like real terrain because it was all just one intensity and didn't look natural. It looked kind of blobby or bubbly. So I did some further researching, and was led to my final version of noise. Apparently, there is a version of Perlin noise that takes a really low intensity of noise, lots of smoothing iterations, as you can see here, and a really high intensity of noise, very few smoothing iterations, like here. And it combines them together to create multi-layer Perlin noise that has lots of very small variations, but also big fluctuations. This is way closer to real-life terrain, as it represents large erosions like earthquakes, and also smaller erosions like water or wind. The feature to make it look like terrain is in the code I uploaded, but you have to turn it on through a variable. I explain how in the comments, but I almost think the plain multi-layer Perlin noise in grayscale looks better. In conclusion, through this project, I expanded my knowledge of programming and problem solving, and had lots of fun along the way. I even had this amazing work of art to show along with it. Thank you.